Alright, this is the homework to go along with 6.1. We'll go through, I don't know, we'll see however many we get through. It says identify the line. Remember, there were 4 special segments. So these dotted lines have special names. So in this scenario, this dotted line is perpendicular to the side. It is bisecting the side, so we're going to call that a perpendicular bisector. We'll put B for that. For 2, obviously it's cutting the angle here into 2 equal angles, so that's an angle bisector. That would be A. 3, again, perpendicular and bisecting the side, going through a midpoint. Midpoint would be bisecting, so perpendicular bisector. 4, we're connecting a midpoint to a median, or a midpoint to a vertex. That's called a median. It's not perpendicular. Alright, that's a median. 5, midpoint to vertex. That's another median. 6, vertex at a right angle. It's not bisecting. This piece is not the same as that. It's not bisect. It's not a perpendicular bisector. That would be an altitude, or C. This one is perpendicular, and it's going through the middle of the side. So this is a perpendicular bisector. Looks like these 2 angles are the same, so that's an angle bisector. And in this scenario, we've got vertex and making a right angle. It's not bisecting. That's called an altitude because it hits the vertex. Altitude C. Alright. The figure below, tell which point of concurrency. That's the point. Like, what is this special point called? So let's see what we got here. This is an altitude. This is an altitude, and this is an altitude. So where do the altitudes meet at? So go back to your notes, and you can look up where the altitudes meet, and that would be the orthocenter. The orthocenter is formed by altitudes. Next, what special point is that? Well, let's see what we got. We've got midpoint to vertex, midpoint to vertex, midpoint to vertex. These are medians, and medians make what's called the centroid. You can look on your chart from your notes to help you check that out. Here we've got perpendicular, and it's bisecting the side. So this is a perpendicular bisector, perpendicular bisector, perpendicular bisector. Perpendicular bisectors make circumcenter, and we could draw a circle around that, and that would be the center of the circle, circumcenter. And the last one, angle bisector, angle bisector, angle bisector, which makes the incenter. Again, it's all in that chart. The incenter is the center of a inner circle. Incenter. That's the first page. The numbers are out of order. It's okay. Which point of concurrency is the center of the circumscribed circle as shown? A circumscribed circle, the center is the circumcenter. Circumscribed circle around the outside, circumcenter is the point. Whereas the inscribed circle, that is the incenter. Alright. Next, point G is a centroid. A centroid. A centroid is the special point where, like, if this is 2, this is double. Alright. So it gives us some stuff here. It says that ABC, the triangle AD is 8. Now because it's a centroid, we're dealing with medians. And because we're dealing with medians, we're dealing with midpoints. So if that's 8, that's also 8. So dB is 8. It says A to G is 10. Now this is the longer piece, which makes this 5. G is 5. The entire length from A to E would then be 15. Or E to A would be 15. Anything else? Oh yeah. A to B would be 8 plus 8, which is 16. And what else do we have on here? We have that BE is 10, which makes this 10 as well, because this is a midpoint. So EC is 10 and BC is 20. Alright, let's keep going. A to C is 16. So if this whole length is 16, that's got to be 8 and 8 again. So A to F is 8, and F to C is not a question. It says C to D is 18. This is a little tricky. So you got to think 18, and this piece here has to be half as long as this piece. So what you do is you do take 18 divided by 3. It's got to be 6 and 12. 6 times 2 is 12. It's double. 6 plus 12 is 18. So G to C is 12, and G to D is 6. The point G is the centroid. The point T is the point of concurrency. I think that's supposed to say G. The point G is the point of concurrency of the medians. Whoops, that's supposed to be a G. That's the median thing. So look, smaller piece is half of the larger piece, and we've got midpoints, so 8 and 8. 7. This rectangle represents the Joneses' lot. There's their house. The non-shaded triangular region represents their backyard. So this part here is the backyard. They want to build the largest possible circular pool in their backyard. How would you determine the pool's location? So what you need is you need a circle that fits inside of this triangle. We need to find an in-center. Find an in-center. How do you find an in-center? By making 2 angle bisectors. You take and you bisect this angle, and you bisect another angle, and that finds the in-center, and the in-center is the pool. Well, and this the circle. That ends up being the biggest circle in there that touches each side of the yard. That's where they should build their pool. The Smith Construction Company has been hired to install. I don't know if that was in the picture there. The Smith Construction Company has been hired to install a new water fountain at the Winston Park. They would like to find the best location so that it's equidistant from each of the 3 main pieces of playground. So there is one scenario where you can find something that's equidistant, and that is you find a circumcenter. So it would be find a circumcenter by finding perpendicular bisectors is how you do that. And then the last one, you're a sculptor and just completed a large metal mobile that you want to hang. You want to hang this mobile made of a flat triangular metal plate. String will be attached and suspended. How would you locate the point where the mobile will balance? The balancing point, that would be the centroid of a circle. Centroid of a triangle. You need medians. So to find medians, you do a midpoint, vertex, midpoint, vertex. There it is. There's the balancing point of that triangle. Number 10, name the point of concurrency. What is this special point? Let's see here. What do we notice? We notice that this point, if I go to this side, go to this side, and go to this side, it's equidistant. So it's equidistant to the sides of the triangle. I could draw a circle inside there that would touch each side. That's an in-center created by the angle bisectors. And this one, this point, is equidistant to the vertices. We can draw a circle on the outside. That's a circumscribed circle. This is a circumcenter. The next are up to you. So hopefully you enjoyed this. Hopefully this helps out, and see you later.